Okay, so let's take a look at a concrete example. We want to compute that integral right there. And now let's look at that and see why it's amiable to integration by substitution. First, I have some complicated expression, right? It's not so simple, x to the 5th plus 6. And it's being composed into an exponent to the power of 9th. Well, you could take a look at that and say, well, this looks kind of like a composition, right? I mean, I have an inside function, x to the 5th plus 6, and an outside function, x to the 9th. If you chose these two expressions, right, u is equal to x to the 5th plus 6, and you also have f is equal to x to the 9th, well then you could say that f of u is basically the expression that you see right here. That's f of u. Okay? So that's nice. We could write, instead of writing, this factor in x to the 5th plus 6 to the power of 9th, we could just write it as f of u. And it seems like we could do that for free, but be careful. You also have this x to the 4th and dx you have to contend with. And how do we deal with that? Well, that's the nice thing with that expression, du being equal to g prime d of x. If you take the derivative of u, this is power x to the 5th, and out here it's x to the 4th. So you could basically take the derivative of the inside function and you get an expression that's proportional to what's going on the outside. In other words, we can take advantage of the chain rule, and that x to the 4th dx could be swept under the du rug. Let's do that concretely. So we'll take u and take its derivative with respect to dx. All right, we get 5x to the 4th. Not quite x to the 4th times dx, but that's all right. So this is what du is, and I want to, instead of writing dx in here, write this expression with du. And so, I'll then substitute u and du into the integral for the third step. For my inside function, I have this x to the 5th plus x. That's what I set u to. And x to the 4th dx is not du, but it is 1/5 du, okay? And you could see that from this over here. You just divide by 5 on both sides. If you divide by 5 on both sides, you could see clearly that x to the 4th dx is du over 5. Now, I'll tell you guys about another way to sort of get du into the expression. This doesn't always work, but it does. It can be helpful if you're getting stuck with the algebra. I would say just solve for dx, right? If you solve for dx is equal to du divided by 5x to the 4th, okay? And then you could plug that into that expression right there for dx, and you can see that the x to the 4th will cancel, okay? Now, this isn't exactly sort of mathematically proper, and in the sense that you're solving for this dx when it's not really a variable. So you don't see that being taught in textbooks, but if you're getting stuck on the algebra, you can try it just to make things easier, right? At the end, we want to compute and not prove theorems, formally. So just as a way kind of make things easier if we get stuck, we could keep that in the back of our mind. And it doesn't always work, but it's a way to do that if you're stuck on the algebra. So, okay, we then take the integral of 1/5 u to the 9 du. Now notice, you got this variable u and you're integrating with respect to du. And that's easy, right? The integral of u to, the antiderivative of u to the 9th is u to the 10th over 10. And we add that extra c to represent the family of antiderivatives. And then during the final step, we'll substitute back the expression of x. Okay, so we have an expression for u in terms of x. We substitute that back, and so we'll get x to the 5th plus 6 raised to the power of 10. Okay, and divided by this 1/50th. So this is the final answer. We substituted back to x, and we got our final answer. We will now talk about a method of integration called integration by substitution. And in its basic form, integration by substitution takes advantage of the chain rule to rewrite an integral in a way that will make it easier for us to integrate. So let's start talking about the indefinite integrals. So suppose you have capital F of x being an antiderivative of lowercase f of x. In other words, you take the derivative of capital F of x and you get lowercase f. Now, suppose we plug in a function g of x into capital F of x and we take the derivative. Okay? Here we'll take the derivative of the outside function, and since we took the derivative of the outside function, we got to multiply that by the derivative of the inside function by the chain rule. And since the derivative of capital F is lowercase f, we end up with this expression at the end. Okay? So in summary, how does integration by substitution work? Well, we have all of these steps. So we identify composition of an inner function and outer function in the integrand. Okay? So that's the first step. And this should be pretty straightforward once you do a few problems and get used to it. I mean, usually you'll have something complicated in the parentheses and an outer function. And again, this takes some practice to get used to seeing. And so that's straightforward. Okay? And now here's the crucial part, and this is why you would want to choose integration by substitution. It's the crucial part. Okay? The outer part, what's outside of the composition, this is the composition, this is what's outside, that is the derivative of the, or could be, is proportional to the derivative of the inside function. That's the crucial point with integration by substitution. You need to be able to get everything outside of the composition under the rug of du. Okay? And so we take the derivative of u, and you could see it's proportional to x to the 4th, and that's what's on the outside. And so that's what makes this a successful strategy. Okay? Step 3 is to substitute u and du into the expression. So rewrite the integrand in terms of u and du. Integrate, take the antiderivative, and then substitute back x, the expression for x of u. And that is how integration by substitution works. So in its basic form, integration by substitution starts out in the integrand with an expression that looks like this and can be written in this form, and we work backwards to attain this expression. Okay? And now notice, once you integrate a derivative, well, the antiderivative of a derivative is basically just the original function. Okay? So this is what we're doing. We start with an integral and we try to put it in this form. Once we do, we quote, factor out a derivative from that expression. So now you got this d dx of capital F with a composition of g of x. And the antiderivative of a derivative is the function itself plus the constant. And so this is how integration by substitution works. Sometimes integration by substitution is also called U substitution, because we basically take the inside function, okay, the function that's inside the composition, and set it equal to this variable u. Okay, once you take the derivative of the variable u, you get this du dx equals g prime of x, and you could write du as g prime d of x. Notice here that that would be du, and you would have a u in there for in the composition. And so here's the theorem. Let u equal g of x, where g of x is differentiable on an interval, and let f be continuous on the corresponding range of g. Then what we do is we'll set u equal to g of x, right? And so you'll get f of u. And then now, how do we get rid of this part here, or not really get rid of it, but sort of kind of sweep it under the rug? Well, that's going to be equal to du then, because of that expression right there. And so now, instead of having this complicated part and a complicated inside expression, we could basically integrate with respect to u and have we would just be looking for the antiderivative of f. And so this is how substitution, integration by substitution works. We're basically taking advantage of the chain rule and a composition in order to integrate just the outer function. Okay, you could think about it as kind of like sweeping the inside function under the rug at the expense of also sweeping this under the du rug. Okay, that's just some way to think about it. More formally in the future, especially when you start doing integrals with multiple variables, you could see that in its essence, integration by substitution is a change of variables. Let's now take a look at definite integrals. Okay, so before we were looking at indefinite integrals, so we didn't have bounds, and now we do. So the rule looks similar to above, except now our bounds must change. Okay, so if we're going to integrate with respect to u, we got to change the bounds, and we got to substitute the bounds into the expression for u. Okay, just pretty straightforward. So we want to compute this integral. Now this is a definite integral. It's the same one we had above, except now we are integrating from 0 to 1. Well, what changes is now we have this u of 0 and u of 1. What is u? X to the 5th plus 6. So plugging 0 into x to the 5th plus 6, you get 6. And plugging 1 into x to the 5th plus 6, you get 7. And you integrate through these new bounds, and you get that expression right there. Now, alternatively, if for some reason someone just refuses to change the bounds, well, you could substitute back. So once you integrate, you could substitute back the expression for u in terms of x, and now you have an expression in terms of x, and you could use the original bounds. Okay? So you could use the original bounds if you substitute back for x, or you could just integrate with respect to u and use the updated bounds. Both of these work, and they give the same answer.